and welcome to the first installment of Perimeter's somewhat reimagined public lecture series. Of course, it's only public in the sense that it's online. Tonight, I'm not standing in front of a packed house in the Mike Lazaridis Theatre of Ideas at Perimeter Institute in Waterloo, Ontario, Canada. No, I'm at home. My name is Greg Dick. I'm the Executive Director of Advancement and Public Engagement at Perimeter Institute, and it is a pleasure to welcome everyone here this evening to our conversation. The public lecture series at Perimeter is Perimeter's longest running outreach program. And Perimeter, as you some know, is a not-for-profit charitable organization. And these public science events are part of our commitment to sharing exceptional engaging science, even when we have to improvise now and then. Our first lecture was given nearly 2 decades ago. And since then, free tickets to attend the in-person versions are typically snapped up within minutes. So today, thank you to everyone for joining us instead online in this new stay-at-home reality. Whether you're a longtime viewer, and I know some of you go all the way back to the very first lecture, or a first-time guest, welcome. Thank you for joining us tonight. We may be physically distant, but we can still do some physics together. So this is new for us, so it'll be a little bit different. It'll be part conversation, part scientific talk, part Q&A, live Q&A, and part whatever else happens. But before we begin, let me say a big thank you to an amazing team behind the scenes making this all possible. And if there are any glitches, apologies ahead of the curve. We will keep on trying and we'll make it all work. All right, let's have some fun. Tonight, we are joined by cosmologist Dr. Katie Mack. Many of you know her by her Twitter handle @AstroKatie. She's an assistant professor at North Carolina State University, and her research investigates dark matter, vacuum decay, and the epoch of reionization. We are delighted that she is currently spending time here at Perimeter as a Simons Emmy-Noether Fellow. It's a program that supports early career physicists. And tonight, we'll be talking about the end, and maybe the beginning, but certainly the end of the universe. Katie, thank you so much for joining us and being willing to give this a try.
Thank you for having me. It's great to be here.
I am excited. Katie, we have Twitter open, and we'll be keeping an eye on the hashtag #PILive. We also have some people behind the scenes, hunkered down in their own homes, watching to make sure we don't miss any questions. And audience members, if you're in the YouTube chat session, hello, be kind, and know that you too can ask Katie questions through me using the same hashtag. And finally, Dr. Kelly Foyle and Dr. Damien Pope will be taking part in the social media conversation, also at hashtag #PILive. All right, so Katie, where is here for you?
Here right now is Waterloo, Ontario, just a few blocks from the Institute. And I'm very happy to be in Waterloo. I wish I could be at the Institute, but we all have to do our part to keep everyone safe right now.
We do, and am I right in thinking that this mandatory seclusion may even have a bit of a silver lining for you? I believe you're putting the finishing touches on your book.
The book is more or less done. The book is I have an advanced copy right here. I believe you do as well. There are little tweaks that I'm doing, and I'm writing some articles that are connecting to the book. So there's some of that work going on. But I thought when you said silver lining, I thought you were talking about the foster cat. So I do have a cat who's asleep on the floor at the moment, who's hanging out with me to keep me company during this time.
That sounds good. And if the cat has anything to say, you bring her right up. That's for sure. Well, all right. So tell us, why did you decide to write the book? I know you're very well known for your ability to pack a punch into a single tweet. Is this a new way to communicate?
I've been doing science writing for a while. I started when I was in college, just finding ways to talk about physics and astronomy with the general public, finding ways to take what I was really excited about as a scientist and bring it to other people, because I find that it's really hard to not talk about it when there's some cool new idea that I've come across, or when I've learned something new about the cosmos. I just really want to share that with people. And the way the book came about is, I was thinking about what kinds of things I like to talk about with the public, what kinds of things are fun to write about. And I noticed that there are a lot of people writing books about the beginning of the universe and not so many writing about the end. And I thought it would be really fun to write a book that really gets into where we're going, what's going to happen in the very, very far future. Our universe has a finite time, a lifetime potentially, and what does that mean? And how do we know that? How are we studying that? What are the possibilities, and how are we trying to find that out? So I thought that would be a really fun way to get into a lot of cosmology, a lot of how we understand the universe, what we're learning about it from observations and experiments, and then what does that tell us about our place in the cosmos and where we're going to be in the future? What is our legacy in this bigger space?
Oh, that all sounds good. I'm looking forward to diving in. Just before we do, now that you've done all of that, and that's such a scope, uh, how does the process feel? Having interviewed some of the most brilliant minds in physics, some even at Perimeter, and now that you've pulled it off, how does the view feel from the summit?
It's great. It's been a really fun process. I know that writing a book is hard work, and a lot of my friends who are authors talk about how much of a slog it can be. Especially as you're wrapping it up, and it definitely was a lot of work. But I really enjoyed it. I really enjoyed finding new ways to talk about these ideas. And toward the end of the book, I have a few sections about like how are we learning this now, like what kinds of observations are we doing, what kinds of experiments, where are things going on in the theory side of things. And so in order to write that section, I went around and I talked to a whole lot of other physicists. I got a grant from the Sloan Foundation to go and interview people, and so I went all over the world and talked to some of the leading physicists in observational cosmology and in experimental physics, in theoretical physics, and tried to get some idea of where everybody thinks things are going, what people are really excited about, and what the process is. And that was just so much fun. I talked to some really amazing people, and I also got to ask some really fun questions because I'm talking about the end of the universe. So I got to ask things like, how does the end of the universe make you feel? What does it mean to you that we're all going to be forgotten at some point when the universe ends? Do you think that's even going to happen? What does it mean to you as a person to think about your legacy in this larger cosmos? So getting those perspectives was a huge amount of fun, as well as just
Well,
learning a lot more about the topics.
I think it's time to get into the science. And just before we do, I do get to confess, yes, I've had the privilege of reading a pre-published version. Just for everyone out there, it's The End of Everything, Astrophysically Speaking. We'll plug this at the end. Again, Katie, it's awesome. Like, it's
Thank you.
awesome. Your voice just comes through. Congratulations. It's
Thank you
terrific.
so much.
It's terrific. So let's jump into the science.
Okay.
The end of the universe. What's the best case scenario? How much time do we have?
Well, I'm not sure how to talk about the best case scenario. There's no way this ends well. When you're talking about the ultimate destruction of all reality, it's not going to be pretty. The scenario that I would say is the most likely, and also the one that would be sort of longest in the future, is called the heat death. And that's the idea that right now the universe is expanding, and when I say the universe is expanding, I mean that the galaxies are getting farther apart from each other. So it's not that this room is expanding, the Earth is not expanding, but the space between our galaxy and distant galaxies, that space is getting bigger, and galaxies are all kind of moving apart from other galaxies as long as they're not sort of in the same cluster or group or whatever. And so as the universe is expanding, we're getting more and more empty space in between all these structures. And we've known this for a while. We've known that the universe started out a lot denser and hotter in the Big Bang, and it's been expanding ever since. And we thought for a long time that the expansion of the universe should be slowing down because there was some kind of bang that started off the expansion, started things moving apart from each other, but all of the galaxies in the universe have gravity and they should be kind of pulling back together, and that should be slowing down the expansion. And so we figured, let's go measure how quickly that slowdown is happening. And when it was actually measured, it was found that it's not slowing down. The expansion of the universe is actually speeding up. And we don't know why that is, but whatever is causing it, we call that dark energy. And we think it's probably just a property of space called the cosmological constant that means that the universe continues to expand and accelerate in its expansion. And so if you extrapolate into the future, that means that galaxies are going to get so far apart from each other that after a while, each galaxy or group of galaxies is going to be kind of isolated on its own and not be able to even see other parts of the universe. They're going to be taken so far away so quickly that each little sort of region of interesting space is going to be isolated from every other. And that means that over time, there will not be these galaxy collisions that bring new gas in to make new stars. And so the stars in each galaxy will start to burn out, and the particles will start to decay, black holes will evaporate, and over time, you end up with this just cold, dark, empty universe. And it takes a very long time. But that's the idea behind the heat death, that eventually you end up with a universe that has basically nothing in it, and a tiny bit of like waste heat from the decay of everything.
Oh.
And that just kind of persists.
That's a little depressing.
It's a little sad. Yeah, it is a sad idea. It's funny when you talk about this, people have really strong feelings about the idea that we're just going to fade away. And even physicists, when I was talking to people about how does the end of the universe make you feel, a lot of cosmologists said, I don't like this idea. There has to be something better that could happen. And there are other possibilities. And I talk about 4 other possibilities in the book, even though the heat death seems to be the most likely based on our current understanding. There's a lot we don't know, and there's a lot we're still trying to figure out, and it's possible that things could go another way.
How do we know that the universe is expanding? Maybe let's...
Yeah, so the way we know that the universe is expanding is that when we look out at distant galaxies in every direction, they all seem to be moving away from us, the really distant ones, and the more distant, the faster they seem to be moving away from us. And that makes sense if just the whole space is getting bigger, because that means that, 2 galaxies that are close together are getting a little bit farther apart over a certain amount of time. 2 galaxies that are already far apart over the same amount of time, they get a lot farther apart. So maybe I can draw this. So
yeah, let's pull out the chalk.
This chalkboard thing is so much fun. So if you have, galaxies here, at some early time in the cosmos, and then the whole space gets bigger, each galaxy is still the same size. The galaxies themselves are not getting bigger, but the space in between each of those galaxies has gotten larger. And that means that the ones that are a little bit closer together have gotten a little bit, less distance. So let's say there's one right next to this one here. Over that amount of time, these ones have gotten a little bit farther apart, and these ones have gotten a lot farther apart. And so the basic idea is that as the universe expands, if it's expanding the same way in every direction, then the farther something is now, the more quickly it'll seem to be moving away from you. And that'll be uniform everywhere. Everywhere will have that same property, that it looks like things are moving away from you faster and faster, the farther and farther they are.
Oh, the heat death. All right. Well, let's go to an online question. I have at KFAB News asks, Dear Astro Katie, could the universe end like right now, or now, or now?
So I don't want to alarm anyone, but as far as we know, yeah, probably it could. The reason that I say that it could, and I, don't worry. Probably it won't. We have good reasons to believe it won't. But there is one possibility for the end of the cosmos that does involve a kind of very sudden, unpredictable, destructive event that could spread throughout the cosmos and destroy everything. So this is actually my favorite way for the universe to end, partially because it could happen at any moment. So this is called vacuum decay. And the idea behind vacuum decay is that maybe so one way I like to explain it is that there's a sort of manufacturer's defect in the universe itself. So the idea being that the way that the laws of physics are set up, the structure of physical law, the structure of how particles interact, the sort of the fields that govern how the cosmos works, those might be in a sort of configuration that's not quite stable, meaning that there's one way of thinking about how the laws of physics are put together. There's the way that seems to be in place in our cosmos, but it's possible that there's a different possibility, a different set of laws of physics that would be more stable over the long term in the universe. Okay, so one way to think about this is like, imagine that you have something sort of balanced on the edge of a table, something like that, right? So this is stable enough, but there's a place that this thing would rather be, which is on the ground, because that's a kind of lower energy state. It's a more stable state. But if this does fall to the ground, that's going to make a mess. It could break. Bad things could happen. And there's a sort of sense in which our cosmos is in that not quite stable state. Like we're okay for now. The way that the laws of physics are set up now are fine, but there's a different set of laws of physics that would be kind of preferable from some kind of energy sense in the larger cosmos. And it all has to do with the Higgs field. So we know about the Higgs boson is this particle that the Large Hadron Collider detected in 2012, and the Higgs boson is related to the process that allowed particles to have mass in the early universe. And that process was called the Higgs mechanism. There was this sort of rearranging of the laws of physics in the very early universe that put us into the set of laws of physics that we have today. And it's possible that there's a different rearrangement that could have happened, or that could happen now, that would be sort of preferable in some sense. And if the Higgs field goes to that value instead of the one it's at now, then that could end up destroying the universe. So the Higgs field is this kind of energy field that pervades all of space, and it has some value that you can talk about as like the amount of energy in the Higgs field that's in this sort of all-encompassing space. And there's a possibility that the Higgs field would kind of rather be at a different value. And if it were at that other value, that it would change all the laws of physics, and that would be a place we cannot live. The constants of nature would be different. Atoms wouldn't hold together. All of space might collapse. And so you might ask, okay, so if the Higgs field took a different value, how would that happen? And one of the reasons that people have thought about this and talked about this for a long time is because there's theoretically, if we are in this so-called metastable state, then a really energetic event could happen that could kick us into this other vacuum state, this other state of the laws of physics. And that the idea there is, I'm going to draw a picture because I'm doing too much hand waving. So the idea here is that these are kind of these two valleys that the Higgs field could live in. And you can think of it very much like a ball rolling around in a hill, right? And these values are different values of the Higgs field, and they have sort of different energy states, right? And if our Higgs field is here, then that's fine. That's perfectly reasonable. But in principle, some very high energy event could kick that Higgs field over that valley, over that hill, and we could end up in this other valley. And this is the true vacuum. And this is the false vacuum. So if we live in a false vacuum, then some high energy event of some kind, say a particle collision, in principle, could kick that Higgs field over into the true vacuum, and we cannot live there. If the Higgs field takes this value, everything is over. That's it. Fortunately, this is too high a barrier. That there's no way to make an event that energetic that could actually do that. So you'd think that we should be fine. It should be not that big a deal that we're in this false vacuum. Everything's okay. We're perfectly stable there. But unfortunately, quantum mechanics comes in and ruins everything. So the problem with quantum mechanics is that quantum mechanics involves the possibility of so-called quantum tunneling, which is this idea that, if you have a particle, on one side of a wall, in principle, it can't go over that wall unless you give it a lot of energy. But because quantum mechanics says that particles are really just these sort of distributed waves, sometimes they can kind of leak through barriers. So imagine it's not a particle, it's a wave, and some bit of that wave can leak through that barrier called quantum tunneling, and the particle can end up over there without having to go over the barrier at all. And quantum tunneling is something that happens all the time in the real world. We have to take it into account for things like flash memory, for certain kinds of microscopes. It's just when we observe an electron on one side of a wall, sometimes it ends up on the other side of the wall without seeming to have gone around. It just sort of happens to go through. And unfortunately, that can also apply to the Higgs field. So this perfectly stable Higgs field in the false vacuum can, with some very low probability, tunnel right into the true vacuum, and we can't live in a universe that has a true vacuum.
Katie, can you give me any solace as to that this isn't going to happen, or?
Yeah, well, I can give you solace in a few different directions. So one is that every quantum tunneling event has associated with it a time scale. So you don't know when tunneling is going to happen. You don't know for sure if it's going to happen, but you do know that over a certain time frame, it's more or less likely to happen. And if it's a really high barrier, it's going to take a really long time before you think that it's likely for that to happen. I mean, this could tunnel through my hand onto the floor. It's just very, very unlikely. It would take a really, really long time. You'd have to wait watching it before you'd expect to see that happen. And fortunately for this process, for vacuum decay, that decay time is something like 10 to the power of 100 years, so or even more. So we think that it would take much, 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 much longer than the age of the universe for this to be something that would be likely to happen anywhere in the observable universe. So that's one reason not to worry about it, even though it could technically happen at any moment right here. One reason not to worry about it is that it would probably take a very long time. Another reason not to worry about it is that we don't know for sure that this process can even happen. The idea that we are in this false vacuum is one that's supported by experimental results from things like the Large Hadron Collider, but we don't know for sure that those experimental results, that those, the theories that those are based on really do extend to the kinds of energies and timescales and so on that we're talking about here. So it's very possible that some other physics will tell us that we can't be in that false vacuum after all. And another thing, if this does happen, the way that it happens is that the place where that Higgs field does its quantum tunneling, that place will be the nucleation point of a bubble. So that'll create a bubble of this true vacuum, this different kind of space that we can't live in. And that bubble will expand, and it expands at about the speed of light until it sort of destroys the entire universe. And the reason why that should be reassuring is because if something is moving at the speed of light, you don't see it coming. And if it hits you, you also don't feel it because your nerve impulses don't travel that fast. And so, this giant bubble of death is actually not that scary if it does happen, because you don't really notice it. You don't feel it, you don't see it. Nobody's going to miss you. There's no FOMO, like it's just over. It's very clean, and there's nothing you can do about it anyway. So I think that even if it is the most kind of dramatic end to the universe in that sense, it's also totally painless and definitely not something to be concerned about. But it is a fun idea, and it's a fun thing to think about as a physicist.
Oh, I feel much better. All right. So if that's maybe your favorite, which is your least favorite, if that's possible?
Mm, I think the one that I would find most unsettling would be the Big Crunch. So the Big Crunch is this idea that's been around for a very long time. It was considered to be the most likely one, sort of in the 60s. And the idea behind the Big Crunch is, right now the universe is expanding, galaxies are getting farther apart from each other. But maybe that expansion will turn around. Maybe at some point the universe will start compressing and everything will get closer and closer together. And instead of space getting bigger, space will be getting smaller, and everything will be more and more compressed in the future. And that would lead to a big crunch, which would be sort of like the Big Bang in reverse. So instead of everything being very, very dense and hot and expanding and cooling, it would be everything is currently cool and kind of diffuse, and it would be growing in density and growing in temperature. And the reason that one is very unsettling is because you would see it coming. You would see other galaxies coming toward us very quickly. You wouldn't, galaxies coming toward us itself, that shouldn't be too scary. We actually know of a big one heading toward us right now. The Andromeda Galaxy is our nearest neighbor, large spiral galaxy, and it's heading toward us right now at 110 kilometers per second. It'll get here in about 4 billion years. And that part isn't the scary part, because when galaxies collide with each other, there's actually so much empty space between stars, even with a head-on collision of galaxies, that the idea that any two stars would collide is very unlikely. And so even when the Andromeda Galaxy comes for us, the solar system will basically be okay, most likely. One thing that can happen when galaxies collide is you get a bunch of gas coming together, and that creates new stars. And so you can get this sort of burst of star formation. And so you might want to worry a little bit about, a stray supernova going off too close. But for the most part, you're probably going to be okay through a galaxy collision. But the place where it gets really unsettling is that as the galaxies are moving closer together, as you have more of these collisions and the space between things is getting smaller, all of the radiation, the ambient radiation floating around in the universe, some of it the leftover light from the Big Bang, and some of it the light created by stars and things in the meantime, all of that's going to be compressed too. And so right now, the ambient background radiation in the universe is very, very cool. It's just a few degrees above absolute zero, about 3.7 Kelvin. But as the universe compresses, heading toward a big crunch, that temperature is going to go up, and that radiation is going to become harder radiation. And there's going to be higher density of radiation, and over time, the wonderful calculation that was done about this by Martin Rees and others in the 60s. Over time, the thing that's going to happen is that the ambient radiation is going to get so hot, it's going to start like burning the surface of stars. Like there's going to be thermonuclear explosions all around the surfaces of stars just from the ambient radiation from the universe. And so once that starts happening, everything else is cooked, right? And so it's this idea of just being sort of slowly baked by the ambient radiation of the universe as you approach a big crunch. So that's a very unsettling notion,
Yes.
and I find that much scarier than the vacuum decay that could just we just poof out at any moment.
Yeah, that's a bit gruesome. The online feed is starting to light up, and a lot of questions about they want to get to know Dr. Katie Mack a little better. So maybe let's shift gears a little bit, and we'll switch to some other questions. And in fact, I'm going to take the liberty to start. I saw a recent tweet of yours, you at 20. It was an image of you throwing a javelin and doing a high jump. And I learned something amazing, which wasn't actually surprising, but you are a track star. You held Caltech records in both high jump and heptathlon. So can you tell us a little bit about that and balancing track stardom and physics life? How'd that go?
Well, I was always kind of a sporty kid growing up. I did a lot of track and field, and I did basketball and stuff like that as a kid. And so when I got to Caltech as an undergrad, I played basketball for one season, and I also did track and field for all 4 years. And it was a great was a great environment to do varsity sports at Caltech because there wasn't that much competition to get on the teams. So it was
I don't believe
that was
that.
helpful. Definitely
Yeah, I don't
you
believe
get your spot. Um, but it was also just a nice way to not burn out my brain entirely by doing physics all the time. I think it's really important to have other things that you're interested in, other things that you do with your body and with your mind to keep some kind of balance. So yeah, so I did a whole bunch of events in track. I did high jump and triple jump and javelin and hurdles, and then I took up heptathlon and really enjoyed that. So yeah, it was a fun thing to do, and I really enjoyed having that as a part of my life when I was an undergraduate.
Of all the sports, was there a fave?
Um, all the events in track, you
Yeah, the
mean?
events. Yeah.
Yeah, I really enjoyed high jump. That was just because you get to fly through the air for a bit, and then you land on this big fluffy mat, and you can lie there for a little while. Yeah, I enjoyed that one a lot. And javelin was fun too, just throwing spears.
Perfect. Um, all right. Speaking of Twitter and people getting to know you, you are a Twitter star. You have a few 100,000 followers. So can you tell us, A, how did that evolve for a
Mhm.
cosmologist? And then secondly, do you feel any responsibility that comes with that stardom?
Sure, sure. Yeah. So the way it started was when I was a postdoc. A colleague of mine was using Twitter to live tweet meetings and to tweet about physics, and I thought that that was a really cool idea. He visited Cambridge when I was a postdoc there, and gave a talk and put his Twitter handle on the title side, and I thought that was revolutionary at the time. And so I thought this could be a fun thing to do. It could fun new way to talk about physics. And so I started doing it, just talking sort of at a physicist level, with live tweeting meetings and stuff like that. And some of my colleagues' followers started following me, and it just kind of started to build up. And then I realized that it was a really great way to connect with people outside of academia and to talk about science in a sort of concise and simple way, where I could try and bring people into what I was working on and what I'm thinking about, and talk about results that are coming out, talk about ideas in physics and astronomy in a way that not just is not just saying here's the answer, but also talking about how we as scientists think about these questions, and what the context is behind these discussions and these discoveries, and how that all kind of fits together. So it was a nice way to really connect with people, find out what people are interested in, what kinds of topics are confusing, what kinds of topics are exciting, what kinds of analogies work, what kinds of discussions are productive and which ones aren't. And so that was a really fun thing to get into, and it just kind of kept going, and it's been building up over the years. And there have been a few events where I get a whole lot of followers all at once, but it's just something that it grows. People really like to talk about science, and they like to connect with scientists, and I've definitely found that it's a way for me to do science writing, but on a sort of different scale and in a much more interactive, engaging way. And you asked about responsibility. I definitely do find that it's important when you have a really big platform to think about how what you say is going to be received. Think about what you're presenting to the world, how how you can be responsible with what you say, and how you say it. And so I certainly think a lot about that. I take that very seriously. I don't I don't go around like making fun of people who are like just random people out there, and stuff like that. Like there's I try and be very aware of the difference between somebody who has a really big platform and somebody who doesn't, and how that can affect people. So I try and be nice. I try and be helpful. I try not to. Uh, share things that I don't think are reliable information. All of that kind of thing I think is very important.
That actually leads nicely to a question from the online feed from @KeithDonnelly19. Uh, he says, as a science communicator, how would you get evidence-based ideas across to people who may distrust the experts or even be anti-science?
Yeah, so that's something that people think about a lot these days. This question of trusting experts, the question of pro science, anti science. I think that one thing that is important to talk about is most people really do trust scientists for the most part. Most people like science or think science is a good thing. The place where it sort of breaks down is that a lot of times people have different ideas about the motivations of scientists in certain areas, or sometimes what scientists are saying can be contradictory to somebody's values in certain ways, and that can make it harder to get an idea across in a way that will be acceptable and useful to the person you're talking to. And so I think that the most important thing is for as a science communicator, I think the most important thing I can do is to talk about how we work as scientists, so that people don't think that we're just sort of saying, here's the facts, you have to accept this because we're smarter than you. You never want to do that. That's not helpful. That's not how science works. We want to talk about, like, we are people who are excited about an idea. We are people who are trying to learn something new, trying to find the truth. We are very dedicated to what we're doing, and and we have all of these processes that are built in to try to make sure that what we're the results we present are reliable, peer review, all of that. And so I think that building trust in scientists, or at least allowing people to understand who we are and what we're doing and what drives us, is a really helpful thing that we can do as scientists to try to break down some of those barriers and make it clear that we're not just there to make people feel dumb or whatever. Like, it's not about that. Like, we are really trying to understand the world and share that understanding.
That idea, that process of science. I remember in your book at one point you talk about, and I think it's related. You talk about the original theory of inflation and how, although it was actually wrong, it was really a good example of science in action. Can you maybe explain really briefly what the physics was there, and
Sure.
then describe how that illustrates the process of science?
Sure. So the idea of inflation is the idea that in the very early universe, the universe expanded very, very quickly for a very short time. So there was this period of a amount of time that was like a billionth of a billionth of a billionth of a second, like a very small amount of time, where the universe was expanding just extremely fast. And we came upon this idea as a physics community in the early 1980s. I say we, it was around the time I was born, so I can't take any credit for it, but this was an idea that was first presented by Alan Guth and some others. And the idea was that this rapid expansion in the early universe would answer some of the sort of very difficult questions around what we see in the cosmos on the largest scales. And the idea of this rapid expansion certainly does seem to answer some of those questions, depending on who you ask. There are people who don't buy it, but the original idea of how that would work just failed. Like, there was no way to get inflation, this process to end and produce the kind of universe that we see now. The idea of rapid expansion worked, but the details were just wrong. Like, the mechanism didn't work. And so over the next few years, other physicists collaborated and came in and developed what was called new inflation, and refined this idea and came up with ideas of inflation that had a similar kind of effect of this very rapid expansion, but through totally different mechanisms. And that was one of those. I was using it as an example in the book of an idea where, sometimes you come up with a possibility and say, hey, maybe this is the answer, maybe this is the way that the universe works, and then you test that idea against data or against just consistency of the theory, and you find actually this totally fails, but there's some seed in that I can pick at and work on, and I can evolve that idea into something similar that shares some of the same properties but gives an answer that's much more helpful in the kind of long term. And so a lot of ideas in physics happen like that, where you start out with an idea and you find out that doesn't really work, but if you tweak it this way, then you come up with something that does work a little better, and then something becomes a little clearer, the picture starts to fit together in a different way. A lot of our development of theories and our progress is incremental that way, where you start with something that's not quite right, but you keep refining it and you keep testing it and refining it and testing it, and eventually you come up with something that seems to fit the data better than whatever you had before, and that's when you make progress.
And that's so nicely said, because it's that point, it makes progress, and then at some point, I suspect that new data or something new will come and that'll break it, and then you'll do more.
Yeah, that's what you want, right? What you want is you want to come up with a model or a theory that seems to explain what you can see in the data now, and then you want to keep testing it and keep finding new regimes to test it in until you find the place where it breaks, and that tells you what the next theory should be. So, for example, when we talk about gravity, you can start with Newtonian gravity from Isaac Newton, where you can calculate how a ball rolls down a hill, or calculate something sliding down a inclined plane, or even the orbit of a planet around a star, or the moon around the Earth. Newtonian gravity works great for most of the situations. But when we started to be able to observe the tiny changes in the orbit of Mercury around the sun, or when we started to be able to observe the way that space is distorted by strong gravitational fields, Newtonian gravity doesn't work for that anymore. And Einstein came along with general relativity, and this is a total reworking of the idea of gravity. Instead of just forces between objects, relativity says that gravity is the bending of space around massive objects. So if you have a massive object, then the space around that object is curved inward and sort of squished together around that object, and that's what you feel as gravity. The trajectories of things are affected by the curvature of space. So everything's trying to move in a straight line, but if it's moving through curved space, it gets deflected, and that's why you get orbits, and that's why light can bend around massive objects like black holes and even stars and things. And so when Einstein came up with that and was able to test that by looking at the deflection of starlight around the sun during a total solar eclipse, and looked at the way that Mercury went around it, it was clear that model worked better than Newtonian mechanics. And you still use Newtonian physics to calculate, how a cannonball moves through the air, stuff like that. Things on Earth, you still use the old theory because the old theory still works, but it has limits to its validity. And the limits are these sort of extreme regimes where it breaks. And then you have this new theory, relativity, that covers the whole space as far as what we've measured. And right now, one of the big endeavors in theoretical and sort of experimental physics is to try to find where general relativity will break. So where are the regions of where Einstein's idea of gravity doesn't work, and how does that tell us where to go next? And one of the things I discuss in the book is that unfortunately we haven't found that edge of validity to Einstein's relativity yet. We know that it has to be there somewhere, that there has to be some region of sort of the space of all experiments and everything happening in the universe where something will happen that cannot match what Einstein predicted, that relativity has to break down somewhere, maybe in the vicinity of a black hole, maybe at the very early universe, but somewhere it has to break, and that will tell us where to go next with our theories. But right now we don't know where it's going to break, and so we don't know yet where to go next.
Oh, wonderful. All right, we're getting quite a bit online, so I'll just sort of fast fire some questions. You can just give a little faster answers, and we'll see how that goes. Hello, first of all, this is from the YouTube channel, and it's Kitten Mama. So given your visitor on your lap, we'll go with this. Hello, Astro Katie. I can't wait to read your book. What happens to matter when it falls into a black hole? Where does it go? Thank you.
Okay, well, as far as we know, once something passes the event horizon of a black hole, and the event horizon is just a distance from the center where, that's the point of no return. Once things pass that distance from the center of the black hole, they can only go toward the singularity. The singularity being this, hypothetically, this point of infinite density at the center of the black hole. Now, we don't know for sure what actually happens inside a black hole, because the fact that nothing can come out again once it goes past that event horizon means that we won't be able to see whatever happens after that, because any light signal that you tried to send out from inside the black hole would turn around and go back in. So we don't know for sure, but we think that once matter goes into the black hole, it has to go toward the singularity at the center. And for all practical purposes, it doesn't really matter what happens to it at that point, because we only perceive it as the mass of the black hole has gotten bigger. And there are really long and complicated debates in theoretical physics around whether or not any information can be derived from stuff that's fallen into a black hole. This is the black hole information paradox that's been in question for years and years. If you throw a toaster into the black hole and it gets a little bit heavier, can you ever figure out that it was a toaster you threw in and not like a couple of bricks? We don't know what the answer to that is, because we don't know what happens inside a black hole. And there are lots of ideas coming from things like string theory about complicated things that could be happening inside black holes, and ways that information could come out again. But at the moment, we just really don't know. So I think of black holes as basically just a feature of space-time, so space-time being the sort of fabric of space. As I said, gravity can be thought of as curvature of space-time, of sort of, where space gets compressed in some way, and a black hole would be very, very extreme curvature of space-time. Let me just draw a picture of that.
Absolutely.
I just want an excuse to use the blackboard.
Love it.
So you can think of, if you have a massive object, then you can think of space as kind of bending, under that massive object, right? So you can draw sort of grid lines, and the space is kind of dented by that massive object. Now, a black hole would be a place where space is just dented massively, extremely, such that you can't really draw the bottom of that bending. And I've drawn this as sort of a rubber sheet analogy, where the object is sitting on the rubber sheet making a dent in that rubber sheet. You have to sort of add another dimension in your head, because space is not two-dimensional, it's three-dimensional, and so it's more that the space gathers in around an object rather than being sort of pulled down underneath it. But a black hole is basically a place where the curvature becomes really, really extreme. And so you can kind of imagine that the matter is turned into that curvature. It becomes that curvature of space, and it contributes to that curvature, and whatever the matter was, it doesn't really matter what it was anymore, because it's subsumed into this object that we perceive just as a source of gravity.
Great. Here's one. Hey, Dr. Mack, I'm curious if you've learned anything from writing your new book, either something you didn't know about astrophysics or something about yourself.
Yeah, well, I learned a lot writing the book. I'm a cosmologist, so a lot of these topics are things that I've studied in one way or another before, but I certainly did have to do a lot of reading to catch up on where things are at with current research. So I learned a lot about what new telescopes are going to tell us, what new experiments. I went to CERN and I talked to people who work on experiments with the Large Hadron Collider, and I found out what they're excited about. I talked to people who work on telescopes, new telescopes that are being built that are going to study, millions of galaxies. I learned a lot about how these theories got developed, and what we know about things like dark energy and even aspects of the early universe that I've never really dug into before. I learned a lot about those in writing the part about how we got to where we are today cosmically. So there's certainly, I don't know about specific examples, but there are certainly a lot of details about these theories that I learned, and just the bigger picture of how we're figuring this out and where things are going next. I talked to a lot of theoretical physicists who are working on new theories of space and time, and one of the things that came up a few times is this idea that space and time are maybe not really fundamental, not really real in some sense in the universe. And this is not even a new idea. It's something that theorists have been talking about for a while, that maybe there's some sense in which the fundamental building blocks of nature are not space and time, but some mathematical constructs that just make us perceive space and time. And we're sort of caught up in that, but in some sense, space and time are not real, or they're not like what the cosmos is really made of. And I didn't know before writing this book how sort of popular or accepted that view is. I knew that there were people working on this idea, but it wasn't until I was talking to some people, and in one of the conversations I had was with Clifford Johnson, who's at USC, and
Yeah.
we were chatting, and he said something like, "Oh, I'm sure a lot of people have mentioned, that space and time are not fundamental," and I'm like, actually, this is a bigger deal to me than you seem to think it is. This is not a small detail, that space and time aren't strictly real. And then I talked to Sean Carroll, who said, oh, they're real. They're just not fundamental. They're just not what the universe is really made of. And I'm like, come on, and it's these are topics that are mind blowing to me, even as a theoretical physicist.
Wow, that's incredible. Maybe we're coming near 8 o'clock. I wonder if you could talk a little bit about the book writing, and all of that conversation sounds inspiring. We're so lucky to have you at Perimeter. Are you enjoying your time at Perimeter as an Emmy Noether Fellow? And how is that connecting to your research and into what makes Dr. Katie Mack tick?
Oh, it's great. It's I'm really happy to have been accepted into this program and to be able to spend some time at Perimeter. One of the nice things about being at Perimeter is that it's a chance to just really focus on my research and talk to people who are working on related topics and come up with some new ideas. So, right now the building is closed, but I'm still in touch with people and still, remotely attending seminars and things. And before it shut down, a lot of the conversations I had with other researchers were really useful, and I'm trying to continue those conversations and keep it going. So I've been talking to a lot of people about vacuum decay, because it's something that several people around here are interested in and working on, and there've been visitors who've come through who are also connected to this idea, and so I've been cornering people and trying to start new projects on vacuum decay, and I have some leads on places to go with that. So that's been really great, and just being able to connect with so many people who are thinking deep thoughts about cosmology and about the early universe and particle physics. I've really enjoyed that.
Katie, that sounds so wonderful. Is there any last message you want to leave to your adoring fans before we wrap up?
Um, I hope that if anybody is really interested in this topic, that I hope that they'll consider picking up the book, because it's, it's a labor of love. Something that I've worked on for a while. But also, a lot of people have asked me, is this, will I understand this book if I'm not a physicist? And I just want to say, like, it's really written for everyone. I mean, you've read it. Maybe you can corroborate this. It's not written for specialists, but even if you do have a lot of knowledge in physics, hopefully, as I learned something writing it, you might learn something reading it.
I can definitely corroborate that. Katie, this book, not only is it your voice, it echoes, and this is, my job is reading science, and I love this one. Truly, Carl Sagan is weaving through there. It truly, really well done. Congratulations. Thank you so much for being willing to do this and having this wonderful conversation. I can't thank you enough. To the online audience, thank you. Really appreciate the energy and the good questions. Sorry I didn't get to them all. We'll try to shuffle some over to Katie and see if she has time to tweet out some answers. And to parents and teachers, specifically parents with kids locked at home with you. If you look in the description section of the YouTube feed, you will see a link to Perimeter's online resources. There are posters and activities and kitchen physics and an online scavenger hunt that you definitely want to check out with your kids for sure. So do that. It'll fill up some hours, and it's some high quality stuff. Thank you for being part of this public lecture, reimagined as it was. We look forward to next season, reimagined or otherwise. Stay safe, stay healthy, stay home, and we will see you next fall. Have a terrific evening. Bye-bye.